They've all been finalists at the Big Data Bowl. Did you win? Did you win? Oh, so they're only finalists, so it's not that big a deal. So sorry, we couldn't get the finals. They all turned us down, so we're stuck with these guys. That's too mean, isn't it? I'm sorry. Are you coming to attack me over here? I didn't win either. No, thanks for rubbing. All right. I'm also a finalist and also not a champion. All right. So the first speaker we have today is a finalist from 2 years ago, and the 2 years ago it was a talk about it was about lineman play, and this is how do you say that? Bachelder. This is Nick Bachelder. He is from, I'm going to say Duke because it says Duke on his thing. And we should also give Nick a round of applause because you recently finished slightly ahead of me in the Kaggle NCAA March Madness pool. Top 8 won money. He finished 12th. I finished 15th. So once again, we're still just kind of losers. What an intro, Nick. All right. Yeah, and we were definitely not first, so we were also last. So that's the world's greatest intro that anyone's ever given anyone. So let's welcome Nick Bachelder to talk about end of play spatial density estimation in American football. Where are you right now, though?
I'm at Duke.
Oh, you're still at Duke.
Yeah, for 2 more weeks I'm at Duke.
Say 23-ish minutes.
23-ish minutes? Okay, I'm going to set my timer. Okay, sounds good. I like to look at it. I don't know why. Do I have to talk into this? Is that mandatory?
No, I guess not.
Okay. Okay, sounds good. I'm setting my time. Give me 1 second. All right. Like Greg said, I'm a master's student at Duke University in biostats for about 2 more weeks. So I'm going to say that as many times as I can. But I was a finalist 2 years ago in the Big Data Bowl. And then this year I was an honorable mention for mostly this work. This is kind of a part of my project this year because it turned out to be what I spent most of my time on. And that's end of play spatial density estimation, obviously in American football. I think all of these will have to do with American football unless I'm missing something. And also a deep learning approach to estimating spatial player influence. All right, how do I arrows? Down?
They don't teach in grad school.
I know. Hey, which one do you press? Press down?
Oh, right and left.
Okay, sounds good. We'll see if I get that next time. Okay, so we'll get started. So what is end of play prediction and why is it so important? Right off the bat, Next Gen and Amazon and the NFL use end of play prediction for all types of things, right? The most obvious ones being expected rushing yards over expected, first down probabilities, touchdown probabilities, all things that most people have heard of before. Essentially, how many yards are you preventing as a defender? How many yards are you gaining as a rusher? These types of things. So this is obviously an important part of a lot of the metrics that are created for Next Gen and that sort of thing, right? And there's kind of 4 levels of complexity that I like to think of when it comes to end of play estimation. And I'm going to kind of go through those so we can kind of get to where I did most of my work. So level 1 is just making a point estimate for end of play yardage. So all this really is you're taking a set of features, those being movement features of the defense, the offense, the ball carrier. This might be velocities, they might be images, they might be spatial. There's tons of things that these features could be, but really all you're doing is you're feeding them into some sort of model with some assumptions, these being maybe an XGBoost model or a regression model or a neural net, depending on your linearity assumptions and your variance assumptions. But at the end of the day, all you're really getting is a sample mean in some sort of situation. So you're saying, I expect at the end of this play, we're going to end up at the 33-yard line. Basically, where is the tackle? Where is the touchdown? Where is the out of bounds going to happen, right? And you're getting a point estimate. And what I need to emphasize here is this is a mean, right? And that'll be important as we go on. And I'll also say that I would say that this is about 90% of end of play models that I see, right? Because this is all you really need to create most of those metrics that I talked about before. But I'm going to say that I don't think that this should be 90% of use cases. I'm going to say that level 2 should be 90% of use cases. And this is just adding one more component. You're still getting a sample mean point estimate with the same type of models, but now you're doing some sort of confidence estimation for your sampling error, right? So you're doing some sort of bootstrapping or standard error estimation if your model's linear. You're making some assumptions and you're saying, now I can say my sample mean in this situation with this set of features is it's going to be, the play's going to end at the 33-yard line with some confidence, right? And this 95% confidence interval, if I say the sample means between 31 and 34 yards, I'm not saying that the play is going to end with 95% confidence between 31 yards and 34 yard lines, right? I'm saying that the mean is somewhere in there. And that's also something that I want to emphasize as I go on, because that's going to be important. And that brings me to level 3. And now we're at multivariate point estimates for end of play location. So now we're doing the same thing. We're still estimating confidence. We're still estimating error, but now we have some sort of multivariate model. And what that means, multivariate, not multivariable, is we're taking, well, it's probably multivariable too, but we have 2 dependent variables. We have the downfield yard lines, and we also have the lateral yard lines, meaning X and Y, right? And most use cases, you don't need to do this, right? Because usually for most of those metrics that we talked about, you're mostly caring about downfield yardage, right? But we're going to kind of find a use case where this is going to be cool and pretty important. So now you have confidence estimates for X, confidence estimates for Y, but we're still working with sample means, right? So this is the sample mean of where the play is going to end up on the play. And that brings us to level 4, which is what I'm going to talk about. And that's multivariate still. It's still end of play location, but now we're talking about outcome distributions. We're not talking about sample means. We're not predicting a mean. Well, we are predicting a mean, but we're predicting a mean, and we're predicting more, right? We're predicting the actual downfield outcomes. So this is now a distribution. You can think in the Bayesian setting like a posterior predictive distribution, right? And you're saying you can now make statements like, I'm 95% confident that the play is going to end between X and Y yard line, right? We still get expected end of plays, but now we can make statements about exactly the probability that if I take an area on the field, what's the probability that the play ends between this area, right? And we're still going to do confidence estimation, because I already emphasized that I think is really important in all of sports analytics, but in this case, especially when we're working with limited data. But how are we going to model this? And that's what I'm going to talk a little bit more about. So I want to mention some past work. So in the 2020 Big Data Bowl, it was actually a metric-based Big Data Bowl where they had a leaderboard and that sort of thing based on your, it was some sort of loss metric. It was continuous rank probability score. And they had people predict essentially end of play for rushers on rush plays. And credit to Next Gen Stats, Philip Singer and Dmitry Gordeev, they came up with this convolutional architecture where they took some input features and they made a cool set of movement features, and they fed them through a series of convolutional networks. And what they essentially got out was a distribution like I'm talking about. It was discrete, meaning it was kind of a multivariate distribution where you have basically a probability that the end of play is at the negative 20-yard line, so on and so forth, all the way up to 50, right? So it's very high dimensional. But they ended up winning the competition. And there's some pros and cons to what they did, right? The pros, some of the pros being, it's a distributional estimate. So we're to that level 4 level. There are no distributional assumptions in terms of what type of distribution is this. It's a neural net that's essentially just outputting logits in a nonlinear way. And generally, it has a great accuracy in terms of the score that they used in the competition. But I'm going to point out a couple cons. Not that this is a bad model at all. It's probably better than I could do in terms of predictive accuracy, right? But it's downfield only. It doesn't have confidence estimation. And the last one I'm going to talk a little bit more about, and that's the fact that it may struggle with multimodality. And what do I mean by that? So the way that I see the football tackle is by definition multimodal. And what that means is especially on breakaway plays, each tackle attempt is successful or if it's not, right? And if it's successful, then the tackle is going to occur for the mean of that tackle with some variance dependent on yards after contact, right? And if it's failed, then another tackle is going to be successful down the field or they'll score a touchdown, right? And it's going to have some other mean and some other variance dependent on a different yards after contact. So that's kind of shown in this image right here. You see the ball carrier has a chance to be tackled in that first distribution. Let's say it's 60% chance with some variance around that mean. But if he breaks that tackle and continues down the field, then it's going to be some other distribution and so on and so forth, right? And it's not really just going to be a continuous decline like we see here, right? This looks pretty normal. There's a peak and then it's a continuous decline, but that's not really the way intuitively the tackle process works, right? Even though obviously it's a fantastic model for accuracy. So let's summarize. The general goal here, we want to estimate a multimodal distribution of end-of-play outcomes based on current player movement and position. And there's a couple hurdles we have to jump over in terms of our data science process for us to do that. We obviously have to estimate distributions as multimodal. We have to generate input features that capture signal and spatial signal. And modeling must take in features. We have to have a model that take in the features that we design, obviously. And we still need to account for that sampling error that I emphasized earlier. So how are we going to do that? Conceptual solutions in modeling. So that brings us to our first solution, which is a solution for the multimodal data, and that's the mixture distribution. And if you haven't seen this before, the formula can look scary, but it's really not. So I've kind of broken it down here. So the function on the right side is just the density of end of play, right? And all we're saying is that our density is going to be a mixture of k normal distributions, and we cross-validate k, right? With each distribution having some weight, pi, right, or p, it should be pk, meaning what's the probability that this particular tackle attempt is successful. And we're going to assume each of our distributions is normal for simplicity. And then for each normal distribution, we're going to basically estimate a point estimate for the mean in the x direction, the y direction, and then prospective variances for the x direction and y direction too. So we're going to get a covariance matrix. We're going to assume the covariances are 0, also for simplicity because we have limited data. And it's going to turn out to look something like that, right? That we're basically just estimating these means, these variances, and the probabilities of these distributions, which are also shown there. So in order to do that, we need to just generate some sort of spatial input, right? Just like the winners of the 2020 Big Data Bowl did. So I made these things I like to call movement maps. So they basically just represent their matrices of offensive position, defensive position, just different velocities, different accelerations. And it basically turns into what I like to call an 8-channel image. So there's 8 channels here representing these different things. And we can feed this into some sort of model, or we want to feed this into some sort of model to capture the variance that I'm talking about and predict these parameters of that mixture distribution we talked about. So how are we going to do that? Okay, gets a little complicated here, but I'm going to break it down. So in order to do that, there's something called deep convolutional mixture density networks. And they're ways of estimating mixture distributions in a nonlinear way from some input, in this case, image input, right? So we're going to take our movement feature maps, and we're going to run it through an autoencoder. And if you've never heard that word before, the way I like to think about it is we're basically taking a bunch of information and we're reducing the dimensionality to keep basically signal there. You can kind of think of it as a very nonlinear, like principal component analysis, right? So that's the purple segment there. And we basically get this vector that's an autoencoded version of our movement. And we take that vector and we run it through 3 different neural nets. And that sounds crazy, but it's not as crazy as it sounds, to get 3 different things. And these are just the parameters that we already talked about. And we can talk about them in a way that's not super mathy and really simple, right? So we're estimating our means, our mu's, which just means where are the distributional centers for each possible tackle attempt. And we're going to do that for each of the k distributions. And then we're going to do the same thing for covariance matrices. What's the standard deviation for each possible tackle attempt, i.e. yards after contact? And then finally, what's the probability of each tackle attempt being successful? That's just the mixture in our basically the P in our mixture distribution. And this perfectly fits into all the parameters of that mixture distribution, right? And what we get in return, well, one more step, sorry. There's one more hurdle, right? Which is we still need to estimate uncertainty. And the way we do that is the same way we would for any other point estimate, like our level 1 or level 2 model, right? We're just gonna ensemble model or use bootstrapping, and we're gonna fit maybe 10 of these models, right? And we're gonna basically resample our data for each of the models. So we have, let's say 12,000 plays with 30 frames per play. We just sample 1 frame per play and feed all of those models into basically different reinitialized versions of what I called TackleNet, which is that model on the last slide. And what we get in return is 10 different estimates, right, of end of play distribution. So that's what that kind of the red heat map is there, just bootstrapped versions of a density estimation. And what we get in return is on the right, which is basically a distribution with confidence, which is the shadow, over the course of the entire field in the X and Y direction of basically the density of where the end of play is going to occur. And we can kind of visualize this for an example here. So here's Saquon making a breakaway tackle, right? This is a great example of why multimodality is really important here. When he breaks that first tackle, there's no chance he's going to get tackled for that entire mid segment until the end, right? And you can see that in the plot here. There's a chance at the very beginning he gets tackled right there, but if he doesn't, it already knows that he's almost going for a touchdown at the very least, right? And that's something that you're not going to capture without that mixture distribution. That's not always the case. So I have another example here. Here's a case where it's not super multimodal, right? And that's why those the mixture parameter is so important. Sometimes your mixture parameter for one of your distributions is almost 1, meaning that you don't have a mixture. And that's still a possibility here, right? Like, we're not saying that it has to be multimodal. We're saying that we're giving our model a chance to estimate multimodality, right? So this is another example where maybe multimodality isn't necessary and those other models might perform just as well. So what's the applications? Why are we estimating lateral field? Why do we need to do this? Is there any real use case for this, right? And there is, and the point is to make metrics, and I feel like that's why we build models for most things. So I made a metric, it's called percent field influence. And the way I did it is I took a spatial, basically you take a density estimation with a player. So that the one on the left is basically a basic density. And then I did the same thing, but I removed a defensive player. And then I subtract the matrices of probabilities to get what I like to call a contribution map. And all that is where is a particular player by removal affecting where the end of play is going to occur. So the red section is where that player is increasing the probability of end of play, and the blue section is where he's decreasing the end of play. So in this case, the play is going toward the direction of like away from you. So he's basically preventing yardage. You can see the blue section is in the end zone basically. So he's probably going to have a high expected yardage saved. And then percent field influence is just the percentage of field area that a defender's inclusion in density estimation influences. So that doesn't mean it's positive influence. It could be negative influence as well. And the point is that it's supposed to capture something different than expected yards saved. Expected yards saved is where is your influence good or bad? This is your influence strong, right? And to make that point, and kind of annotation request, I'm going to decline the annotation request. But what's the relevance to this to tackling? We said the big data was tackling. The point is that expected yards saved and percent field influence capture different variability, right? So if you put both of these metrics in a model that predict whether a player is going to be involved in a tackle, they're both independently significant. And we can say the odds of tackle involvement increased by 243% for each expected yard prevented, which is a metric we've had for a long time, right? But in addition to that, the odds of tackle involvement increased by 6% for each percentage of field influenced. And 1% of the field is about 60 square yards. So you can basically say that for every 60 square yards, if you assume linearity, then your odds are going to increase, linearity of the log odds, your odds are going to increase by 6% of being involved in a tackle, right? So independent variability for expected yards saved and percent field influence. And I have just 2 more examples where you can kind of visualize this if the key will work. Like maybe. Cool. Okay, so here's just 2 examples. So on the left is just the basic distributional prediction of the end of play. This play is going toward the end zone. Ball carriers in red. You can see the mixture density that's estimated for this particular frame. And then I put 2 defenders here that are closest to the ball, and along with their expected yards saved and their percent field influence. You see that the defender on the left, Edmonds, they're both preventing the chances of a touchdown. So they both have positive expected yards saved by removal. But you can see Edmonds is massively decreasing the probability of a touchdown. And you can see that visually in terms of the X and the Y direction from that blue area that he's massively decreasing in the end zone. Jones is not doing quite as much, but you can kind of see how both expected yards saved and percent field influence are visibly kind of different and also capture different types of variability, right? I have this one more example. It's pretty similar to the last one, I just kind of included it to have more content and to like kind of show off what is kind of the point of every bit of math that I just talked about. But I'm going to leave this up while I take questions so that everybody can look at it. But thank you guys so much for listening. I'm Nick, and I forgot to put contact information on here. So if you want my contact information, then just ask. So yeah, thank you guys.
Does this work? I'll walk around with a microphone for questions. I'm not giving you the mic. Does anyone else have a question? Does anyone have a question?
Okay. I have a question about the bootstrap. So you just randomly sample like a frame at the frame level, basically, right? Like, do you have any concerns about that? Like, with something like sampling at the play level or even the drive level be more reasonable? Because I feel like with just sampling frames,
Well, the reason why I sampled frames is because in my mind, each frame in a play is dependent, right? So for my neural net, I want independent observations. And if I'm sampling multiple frames from the same play, then I'm going to have a lot of dependence in my observations, which is somewhat of a assumption killer. But yes, you probably could make bootstrapping potentially better by having more plays and having the autonomy to be able to do that. Again, I also want to emphasize, going along with that question, that uncertainty for a lot of these predictions is massive. And the reason why is this is a big model, right? And I'm using big datable data, which is, again, 12,000 plays in this particular case. So this is a big model. And the idea is that you could run this with a lot more data, and it would be your estimation would be a lot more precise. Your confidence intervals would be a lot smaller. But that's kind of the point of why we estimate confidence, right? I could just throw this up on the board and be like, here's my density. But really, in a lot of cases, and you can see it right here, the density is super variable because we're working with a limited sample size. Even though 12,000 sounds massive, it's really not that big, right?
Does anyone else have any other questions? I'm gonna ask one then. No questions. You showed the multivariate normal distribution with 0 on the covariance. Did you is that an assumption you made, or
it's definitely an assumption?
So you never checked to see. I was wondering if you could talk about like what would the practical implications be of including a covariant structure here, and do you think?
Yeah, so I tried
what it would look like, or did you try it at all, or just too much computation?
I tried it. So I decided at the end it wasn't necessarily worth it because it's a lot more parameters. You're thinking, let's say I select, if I allow k to be up to 10, so which is really high. I don't think I let it be that high. Let's say even 5, right? If I include 2 more parameters per mixture, that's another 10 parameters I have to estimate, right?
Yeah.
And this is a massive model with obviously a ton of parameters here. So it's not just 10 more parameters, it's a bunch more layers with a bunch more information, right? Ideally, if you had more data, you would do that. But to answer your what would that look like?
Well, I don't know if it would actually add that much to the model.
Yeah,
right?
So,
I don't know.
So I did do it, and basically what it does is instead of having just vertically, if I drew on these distributions a vertical line and then a horizontal line, they would be perfectly like this, right? But it would basically allow me to take these distributions and shift them on a diagonal.
Right.
Is how that would look.
Which I think is more realistic. Like I can imagine there being a correlation between, like you get further down the field, you're probably going to be further on average, you'll be further towards the lines because you're going to go away from stuff. But I'm not sure it would add enough to make it all that
in
useful.
our limited data situation, I would say I'm hesitant to do it. If I had more, I would. But the other thing is, like, there's plenty of assumptions here that you can play with, right? Like, and if I had more data, I would. For example, I don't necessarily think that the mixture should be normal. It's just kind of a simple way to kind of implement it for the first time. But really, if the tackle mean is here, then there's probably more of a flashlight type distribution from that sample mean, right? It's probably skewed. So there's a lot of assumptions here for sure that if I had more data, I would love to try new things with. But I will say that I don't have that luxury.
Right.
So
we'll talk to Mike Lopez. We'll see.
I'll send him an angry email and see how that goes.
We'll tweet at him.
Yeah. Okay. Sounds good. But But yeah.
We're going to Mike Lopez's house. Where does he live? He lives in Connecticut.
You
That's
have the
true.
pitchforks or
Yeah.
okay.
With some pitchforks. I have another question if no one else has any questions. I'm just going to keep asking questions until. Just yell. Okay, all right.
I can hear. Yeah. Yeah, maybe like something Laplacian or something like that. There was actually in the lineman big data bowl, there was a submission where somebody used a distribution that was it the Dorito distribution that they called it? I can't remember, but it basically looked like a Dorito. Like it was like the mean was here, and then it was like some gamma normal distribution. Basically, the idea is, I mean, who cares what the distribution is? The point is that the first point of contact, you shouldn't have an equal likelihood of going backwards as you do go forwards, right? So that's, I mean, we can get mathy with it, but at the end of the day, that's what you want. So you're looking for a distribution that does that probably.
Yeah. And I just have a final what so for every play you're not estimating a single K, you're estimating a K for every different play. Or is there?
So there's a set K that you cross validate, right?
Well, what is the value of K that you end up with?
So I cross validated it to be. So I initially cross validated it to be pretty high, but I limited it to a max of 5 because obviously the more mixtures, the more parameters. But the one thing I do want to emphasize, and that was the point of those examples, is that just because you have 5 distributions doesn't mean you're using 5 distributions. It just means for any given play, you have the chance to estimate 5 distributions. But for another play, 4 of them, the mixture values there, the weight distributions of K could be 0, meaning that those tackles are basically completely impossible to happen.
But in cross validation, you chose a value of K. What was that value that ended up
5?
It was 5?
5.
Okay.
I think it did cross validate to be higher a couple times, but I limited it to 5.
Oh, so 5 is not what the cross validation told you. It was you cut it off because computationally you didn't want to fit 10.
I think I did maybe 1 through 10, and it might have selected 7, and I said 5.
And you were just like, okay.
Yeah.
And there was probably not much of a difference between 5 and 7.
Yeah, exactly.
Because most of these are going to be
exactly.
I would imagine most of them are unimodal or bimodal at most.
Yeah, it would have been sacrificing.
Okay, we got to move on.
It would have been.
We're getting yelled at.
Sacrificing bias for variance is what you would have been doing by estimating more parameters, is what I would say. But yep. Anyway. After I finished all this coding, I didn't consider anything else. I threw the code in my backpack and called it a day. But maybe next time.
It's a good idea though. You should look at that.
All right, sorry.
All right. We're getting yelled at. It's time to move on. I don't know. My phone's dead. Who's next? Smit's next? Okay. Smit, our next speaker is Smit Bajaj. Is that right? And you are, I'm going to say, an undergraduate at Duke. NC State. Is it south? Is it down there? Wake Forest. Northeast. No, not even close. NYU. Of course, obviously NYU. This is joint work. Your partner is in London right now. He's living the dream, living the high life in London. He couldn't be here, so you're stuck in stores instead. Not that there's nothing wrong with stores, but stores is great. You have to live here, whatever. I was here for 4 years. Is there anything else you want me to say about you before you? All right, Smit Bajaj is going to talk about. We need to get your slides up, don't we?
Yeah, I think we can get them up.
Do you want to do this?
On the right.
No, you're not fractional tackles. Is it F11? Control F? Control L?
Like the little.
The presentation thing. All right.
There we go.
Smit is going to talk about spatial edge technique, a framework to evaluate edge setters. Please welcome Smit Bajaj.
It's fine. It's fine. Thank you. All right. Hi, guys. Thank you for the incredible introduction, Gregory. I'm Smit, undergrad at NYU, and today we're going to be talking about SET. It's a metric to evaluate edge setters. Curiosity, how many of you are familiar with the concept of edge setting or setting the edge in football? Okay, so just about half, more than half. That's good. So we're going to watch some football and kind of discuss what this process is like. So the first play here, if the GIF will load, which I'm worried it might not. Okay, I'm going to walk through this just with a still image. So you can see where the cursor is at right now. This player is Darnay Holmes. He's the edge setter on this play. Right here's the running back, Travis Etienne. He makes his way over to the left side. And so the defensive back in this position, his goal is to restrict access towards the outside part of the field. Because you can see just off the pre-snap distribution, in the middle is where all the linebackers and interior defensive linemen are. On the outside is accessing space. That's open space that you want to get to. So the job of a Darnay Holmes in this scenario is to restrict access to the outside space. You can see at the top of the screen, it did not happen. Travis Etienne ran for a 49-yard run. And the next example I'm going to show was the opposite, where Aiden Hutchinson, of course, I wish we had the GIF live, but Aiden Hutchinson kind of stormed through the defensive line, restricted Tony Pollard from going to his end. For some numbers on it, changed Tony Pollard's direction by 50 degrees, and he decreased his acceleration by 25%. So he saw him, shuffled his feet, stopped, and then went to the left side, ultimately losing 1 yard. These two plays were very different. The one thing I'd like to point out is in neither of these examples, Aiden Hutchinson doesn't appear in the description here, and Darnay Holmes' name doesn't appear here. But they were very pivotal players to this end result. And so this highlights a broader result, a broader disconnect between the film room and the spreadsheets, where basically they told different stories. On the spreadsheets, on the one hand, Deshaun Elliott got credit for a tackle for loss, and he can go to contract negotiations and say he got this credit for tackle for loss, when in reality, Aiden Hutchinson was the one who impacted the play in the first place. And then in this example, Darnay Holmes kind of gets out unscathed. When he was the one who made the mistake, it was a 49-yard run, but that discredit doesn't come back to him. You can watch film, and if it was loading, you could see, and manually attribute or distribute credit accordingly. But one, this process is very labor intensive. It requires hundreds and hundreds of manual film watching that may be put to better use. And two, it's non-quantifiable. So you can't compare across different teams and see which players are better or worse at this specific task. So our solution was to quantify off-ball contributions. And more specifically, we wanted to see, okay, how well does a player set the edge? How well do they restrict the running back from getting to their intended destination on the outside third of the field? And so we started thinking about it as a film evaluator might. We asked two questions. The first of which is, how well did the edge setter actually get into position? And then did the runner change direction to the inside? Because ultimately that's your goal here. You don't want the running back to get outside of you. You want to force them back inside to where all that traffic and congestion ultimately is. And so we watched film on it, we thought about it logically, and then we kind of moved towards the math. So this is a Voronoi region, and you can basically think of this as what space does a player currently control at a certain frame in time. And so this example was Darnay Holmes, who was highlighted in red. And so you could see, I really wish we had the moving GIFs. I really wish we had it. But you can see as Travis Etienne turned the corner, this Voronoi region kind of grew to the size of what's on the bottom here, and then shrunk to being very little. So basically, we use this as kind of a method of describing how much space does the edge setter currently control. This is a 2D Gaussian distribution. You can kind of think of it as like a highlighter for valuing space. So this is a runners, you take their speed and direction, and you project out where they want to be 5 frames in the future, half a second in the future. So because you can project where the running back's intention is to be, you can project, okay, what space should the edge setter control as a result? And then for us, it was as simple as just overlapping these two. Basically saying, okay, how well did the edge setter get into position? All you need to do is see the overlap on this play. So you can see, for whatever reason, the Aiden Hutchinson score, the overlap percentage does increase. The GIF underneath it, I think it was too big of a GIF. It's not loading here. But in a frame-by-frame scenario, you can see these two start to converge, and then you're left with a percentage. And that percentage is ultimately answers our question of how well did the edge setter get into position. So Aiden Hutchinson reaches, I think, 15% on this play. So with that first question decided, you can move towards the second question, which is, did the runner change direction to the inside? This is more the action phase of our investigation, like what actually happened. So you can see how well you're in position, but now what? And so this middle graphic, I think, displays it well, where this red vector is where Tony Pollard's intended destination was when he received the handoff. Once he saw Aiden Hutchinson, then he kind of veered to the left. And then you can calculate that angle change. I think it was something, it says 32.4 degrees, something along those lines. So you continually calculate, okay, what direction or to what extent did the runner change direction to the inside? And then from there, you can standardize this. We just did a 0 to 1 scale. Anything below 0 means the running back is going outside, and you don't want that. So we just labeled that as 0. And then 90 degrees is a complete perpendicular change in direction, and that's as good as a 1 in our score. And then you just normalize it. So 45.5, 60 would be 0.66, et cetera, et cetera. This one's loading. Cool. Okay. So to get our final score, you take the overlap percentage that we discussed, and now you can kind of see it in a more frame by frame scenario. You take the standardized angle, you add it up. For simplicity, we just added it up, and then you get a final cumulative set score. And I'll let this run because I think it displays kind of our step-by-step thinking. But this is an example of looking at this in the film room, thinking about how to solve it using numbers, and then getting to a number, basically. Because once you get to this number, we just ran basically this iteration through every single play that qualified for this, and you get a ranking of the top players for this. And so this passes the sniff test because you can see Josh Sweat is at top. He's like a 6'5", like 250 run stopper. And the guys on the left generally fit that mold, right? Aiden Hutchinson's there, Montez Sweat's there. These are generally run stoppers as opposed to maybe premier pass rushers. They're still good pass rushers, but it fit the sniff test there. And then on the right side is more binary. This is kind of easy to understand where it's like Brian Burns, 86% of the time, set the edge successfully. So this is a 1 or a 0. And if we go back to the process of this, it's did the edge setter have influence or have overlap? And then did they force the runner to the inside? So you don't calculate the extent to which they did, perhaps. So someone like an Aiden Hutchinson, when he forced Tony Pollard significantly towards the inside, would get a better score. But it calculates just kind of a binary success score. And then this is set GPT that we made before the combine for fun. So you could throw into it and ask, hey, I'm game planning for the Broncos. What should I do? It says to target Bradley Chubb. And if the GIF would run, which it won't, and Travis Etienne got another like 50-yard run here, which you wouldn't expect. Bradley Chubb is a decently good edge defender. And yeah, this was fun. But that about concludes what I'm going to be talking, like what I talked about for the project. Again, I apologize for the GIFs. I think it would have been a lot more intuitive with the GIFs, but feel free to talk to me afterwards or anything about the project as well. But I did want to get into a more personal side of it, which is lessons from the Big Data Bowl and just kind of general like learnings, because it was a very like transformative process from start to finish. And I think there's a lot of kind of takeaways, and I'm sure you two can talk about it as well.
Someone on chat is
Ronald, yes.
Yeah, I just had a question. Hello?
Hello, Ronald? Hello?
Can you hear me?
Yes.
I just had a question.
Yep.
Well, through your research, what do you see as like the big picture outcome for this research, like the practical application of this? Would this be something for the just fantasy players trying to figure out who they should put on their team or their roster for the week? Or would this be something that like a team would use to overlook highlights when they're preparing for the next game? Or would this be something that an opponent would look at to see how to better defend?
It's a good question. I think this is probably one of the best applications you're going to have if you're struggling on run defense, because you notice that, you know, your cornerbacks are getting exposed too often play after play. You're going to want a more quality edge setter. You can find some value within this, where Chris Wormley, for example, isn't going to be super, super expensive, and he might improve your run game or your run defense more than your replaceable person. So I think it's on the team side for the most part. I think game planning as well. This was obviously like a tried example using GPT, but I think the concept remains where Bradley Chubb was surprisingly like 110th out of all edge setters. And you could see why when you look at the next week, okay, like what was happening. He kind of shot inside in this play. So I think for those two things, I think it's definitely team side. I don't think it's consumer side, but it's recognizing holes in an opposing team's run defense. And then from there, maybe you want to make some value adds in free agency. Does that answer your question? I'll take your silence as a yes. Yeah. Okay. So I'll move on to the more personal lessons here, and I'll start with a story. I told you I'm from the Northeast, grew up outside of Philadelphia, go Birds. And about 2 years ago, there was a conference, Wharton Sports Business Conference. And I told you originally from outside of Philadelphia, go to school at NYU. So I figured, why not take the train over? About an hour and a half train, get there at like 9:30, and settle in. And then this man, Mark Lasry, anyone familiar with Mark Lasry? Show of hands. Nice. So one person. I wasn't either. But apparently he was the co-owner of the Milwaukee Bucks. And more I looked into him. CEO of Avenue Capital Group, which is a hedge fund that buys distressed debt. And so he was the kind of keynote speaker here. And more I looked into him, the more interested I was. It's not every day you can kind of have a somewhat personal conversation with a guy whose net worth is like $2 billion and owns and runs a basketball team. And so the conversation went well. At the end, he asked if there are any questions and raised my hand. I thought the conversation was really insightful. So raised my hand and asked like if he had any lessons for someone who's kind of like us, like an undergrad still trying to figure out what to do and kind of how to approach postgraduate career. And he said there's two types of people in this world. He said there's the number crunchers and the storytellers. And the number crunchers think the storytellers are idiots, as maybe some of us do. Because they can tell a story, but it's never grounded in any truth. It's kind of untethered from any sort of reality. And then he said the storytellers think the number crunchers are stupid because you can run the best model in the world, but if you can't explain the results of it, then it's as good as useless. And he kept going on this, there's a binary distinction between the number crunchers and the storytellers. And afterwards, he started talking about professions as well. Like they either fall into one category or the other. And eventually the chat kind of ended, ran out, but this concept kind of stuck in my head that there's kind of two groups of people within this world. And I did like a little bit of like a mock draft in my head. The lawyers go to the storytellers because they talk to people, run a fact pattern, and kind of make up a story about what happened. There's not often very many numbers involved. I'm sure there is, but you get the point where generally they side on storytelling. Hedge funds have moved towards the number crunchers, right? A lot of quant firms, there's billions and billions of dollars being traded on a per second volume nowadays, when previously maybe that was more on the storyteller side. Next up, I guess we're doing a snake draft. We have like software engineers, again, more on the logical thinking sort of side. And then after that, we have venture capitalists. Again, if you're investing in a startup, you're investing in Meta, Airbnb, whatever, you're investing in a story, hoping that story works out and you get rich. And so the more and more I thought about it, the more and more it made sense, where it's like you can be pushed to one side or kind of pushed to the other. And then this was me in the middle. I went undrafted because I was thinking about where I was in here, because I really loved coding, but I liked storytelling. I like to write. I like to kind of express that. And it, like in high school, that was a common barometer that even Lasry said, who was a lawyer himself. He said that if you want to figure out which one you are, in high school, was your favorite subject English or was it math? Mine was English, but I really like to code. I study data science. So where do I fall? And ultimately, thinking about getting a career in sports, I thought about it in a sports setting. You have sales, corporate sales, sponsorship sales. That's more storytelling, right? You're in the trenches dealing day to day with people as opposed to numbers. And then finally, analytics, obviously the theme of this conference, number crunchers. Like that's very clearly, or so I thought, always on the left-hand side on this binary distinction. And I think the biggest takeaway from this competition for me is that it's more of a spectrum. I'm surprised that worked. It's more of a spectrum. It's not a binary distinction. And analytics, I think, is in the middle more than anything else. And I have a little bit of logic, I think, backing this up. This is the Kaggle competition from Google and Two Sigma, more on that left-hand side with number crunchers. The primary score, or the metric here that they kind of grade you on, is an accuracy score. It's a log loss, Brier score, whatever it is. But it's just a very simple score, top to bottom leaderboard, no story behind it. You submit your code, your Jupyter notebook, and then kind of that's that. Big Data Bowl is very different, where I think 20% of it, 25% of it was your submission, was the 2,000-word essay effectively that you submit. And I think 10 to 20% was also in data viz. So it's not just about your Jupyter notebook or what you submit in Python, but it's also how are you expressing it, right? What story are you telling with the data? I think there's three translations you have to make. Versus if you're submitting in a Google or 2 Sigma competition, it's all just your code. Again, you submit your Jupyter notebook, you call it a day, hope to get the best accuracy score and then move on. But here you have to translate it to English because you have to think about it in that kind of logical way. And then you have to make that one more translation, which I think is pretty hard, is translating it to football. And I put a picture of Bill Belichick here because I think he is pretty analytical. But like, if you look at him, you don't think that at all. And so it's like the Bill Belichick test. If you present this to Bill Belichick, would he understand it? Does he care about your normalization of features or whatever? No, he just cares about the output and how well you communicate that. And I think this is an example of like, we did not want to present this because who wants to look at that, right? And we can explain that and it makes sense. And this crowd, I think, understands that more than most, but you want to see the pretty visualization that should move on the right-hand side. Because that's what a coach and player and front office would really understand. There's a lot of actionable takeaway. And I think at least for me, my ego gets attached to the left because you want to show, look, this is the formula I created. I feel so good about it. But in reality, you want to make it look pretty with different visualizations and things of that nature. Here's another example, and this is a still image, so I can explain this one a little more, going back to the big data bowl as well. This is the Darnay Holmes example I brought up in the first slide, but you can see this is the formula we use. It's just a shoelace algorithm. It's nothing too crazy, but again, kind of looks complicated. But in reality, it's just attributing area to a certain player on the field. And then from there, we chose Voronoi regions for the purpose of that yellow line is kind of a leverage line. You can see if that defender is outside leverage or inside leverage. And you don't really need a PhD in math or anything to understand it. It makes a lot of intuitive sense. You see it, where's the angle facing? And then from there, you can determine, okay, what kind of leverage does this defensive back have? And in this case, you can see how much space Darnay Holmes lost. In the frame 30, he controls all of that outside space, as you can see indicated by the red area. And then as what we call the door getting swept open, when he loses his leverage, it gets overtaken by the pulling offensive tackle. I think it was Cam Robinson. And then Etienne got outside and got a 50-yard run. But again, hope this displays the purpose of turning that into what's hopefully actionable and understandable. So this is kind of how we thought about it, where I played football. I was the guy. I was Darnay Holmes when I played. I was on the outside, trying to set the edge because my coach said, if you have to make a tackle, then we probably messed up on the play, which didn't feel too great. But thought about it first in football language, right? Thought like how a coach might. And there was a really, really good video. It got taken down for some reason. I think it was copyright issues. But there was a really good video where all like 32 coaches were talking about this exact thing, setting the edge. And they got really, really animated and excited about it. And so that was good signal to where, okay, this matters. Like we as fans may not think it matters that much, but if they're getting this excited about it, then it likely does matter. So then from there, it's okay. We want to think about setting the edge. Thought back to my playing days, and we came up with these questions. Are you in position, and did you change the angle? Because when you watch the game, those are the kind of thoughts that come in your head. And then afterwards, then we finally moved it to Python or whatever language you use. But then you use the math and numbers to kind of figure it out. And then this workflow worked well for us. And I do think it's football or baseball, but whatever sport you want to think, specific, where you have to think about the problem in a very logical, like application sense first, and then you can move back to using math, using the numbers to kind of get to a sound conclusion. Does anyone know this play? Okay, yeah, just to jog your memory. The article title is, did the officials screw Eagles with questionable holding call? The answer is yes. And I thought this was a good kind of closing slide because it demonstrates the dual nature of it, where the Eagles are seen as a very analytically sound organization. They got to this point, Jalen Hurts was on a rookie contract. Whole point being there, you pay him $4 million. Patrick Mahomes is making $50 million, but Patrick Mahomes is not like 12 and a half times better than Jalen Hurts. So you get some value there. James Bradbury, good value signing. He's on the screen here. And throughout the season, the Eagles made little moves and little changes that contributed to a powerhouse of a season. And meanwhile, the Chiefs, on the other hand, lost their star receiver, come in with Patrick Mahomes on effectively one ankle at this point. But yet, because of a random and arbitrary decision like this on a 3rd and 8, the Chiefs ended up winning the Super Bowl. and then I was really sad that night. But I'd like to emphasize that throughout all of this like solving of the game and using these numbers, a moment like this, or just like very arbitrary moment, where just like a display of human error, human humanity, 50-50, you don't really know, right? Like this thing is unsolvable. And going back to software engineering or quant trading or all these other kind of disciplines, it's very solvable. You get to an answer, you move on, you're very happy with it. Or you get to within a decent confidence interval and you feel good about it. But here, there is no model, there is no kind of number that could have been used to predict this play happening or the Chiefs winning as a result. And so I think this game is very, very random. And I think that's why like it exists in the middle between the numbers and the narrative, because there just is an element of randomness that we can't control. And I think the one thing we did in this big datable kind of process was lean into that randomness. And I think that's why we did well. Yeah, that's it. All right. Thank you, guys.
Does anyone have any questions? Yep.
Hey, I was just curious if your like set grades match similarly to like the run defense grades of like PFF.
Yeah, ESPN has one too. Run block win rate. It did. We ran some like exact analysis to get a number, but qualitatively, yeah, like the names you saw at the top of the list. Another group did edge setting as well, and they presented at the combine. Very shared names, so that I think validated our process.
Anyone else?
Yeah, I have another question.
Yep, go ahead.
You talked about your takeaways from the actual conference itself and what it taught you about the careers and the whole idea of sports analytics as a whole. Do you think that that was something that you wouldn't have figured out it had you not gone to that conference? And is this invaluable information to you now that as you go forward in your career?
Yeah, it's a good question. I think so. Yeah, I think what you learn by doing, and oftentimes you can like try to appreciate the randomness or whatnot, but you really can't. So yeah, I think actually getting in the weeds of a project kind of helped me understand that. This kind of sits in between the numbers and the narrative.
My question is just kind of about like backdooring blocks, like how you showed Darnay Holmes try and backdoor it and fail. But like, what about players like, I mean, anecdotally, like JJ Watt would backdoor the block and get the tackle. Does your metric account for that?
It punishes it if it's not successful, which I think it should.
Mhm.
Again, this example, I'll go back. Last slides. This example with Bradley Chubb, exact situation. I think that's why he got penalized by it so much, because he tried to backdoor it. Maybe he does play. He tried to backdoor it, and it was unsuccessful. Travis Etienne got the edge. So it generally is pretty harsh on it, but I think it should, because that is going to be a risk or reward type of play.
So does it reward it when they do make those tackles?
Because then they're very heavily in the influence area, or they can force running back inside, either or. And we did assign, I didn't get to it. If you did make the tackle on a play where you're supposed to set the edge, you got a score of 1 as well, which is just as good, obviously, as forcing the run in the other direction, because you achieved the outcome.
Thank you.
Yep.
Anyone else? Can I ask a question, or do we have a little bit of time? Okay. You go back to, you have there's the two components of the, I probably asked you this at Big Data Bowl. There's the two components of your metric,
Right.
and you're weighting them equally?
Yeah, so what we thought about doing was manually flagging plays where defender did successfully set the edge, and then weighting these variables accordingly based on which matters more, which doesn't. It's very, again, and this is kind of why we created in the first place, it's a very manual process. So it just became too tedious to flag 50 to 100 exact examples and then kind of get comfortable waiting behind this. But yeah.
Yeah, because I would just think that there's some, I have no idea which one it would be, but I would imagine that like you're basically saying that 1% of overlap is the same thing as 0.01 of an angle.
Right.
And I would imagine that one is more important than the other. I have no idea which.
Right.
But I think that'd be a really cool like next step to make it a little bit more interesting.
Right. 100%.
Yeah.
100%.
All right. Anyone else have any questions? All right. Let's thank Smith. I haven't called you up yet.
It's my turn, so.
Ready for your introduction?
I want it in PowerPoint.
All right, I'll stall. I'll stall for you. Our third speaker in this session is future Dr. Kwong Huynh. Well, maybe not. Maybe you're gonna fill some stuff. Kwong was a undergraduate student at, I don't remember Kwong, Wittenberg University. He was a graduate student. He did his master's at Loyola University Chicago in the Department of Mathematics and Statistics, where I am. The greatest day of my life was when he graduated and left and went to do a PhD at Carnegie Mellon in the Department of Statistics and Data Science. Is that what their department is called now? I've worked on several papers with Kwong. We did some stuff that made the finals at the Carnegie Mellon Sports Analytics Conference. We worked on the talk I gave earlier today was joint work with Kwong. And we did a big data bowl 2 years ago where we made the finals. I was not involved in this one. He dropped me from the team, thought he could move on and be better without me. And he made the finals without me, which is proof that you don't need me to win anything. I've stalled long enough. This is Kwong Huynh. He's going to talk about fractional tackles. Let's welcome Kwong.
All right. Thank you, Greg, for the kind introduction. So yeah, today I'm going to talk about fractional tackles, which is my submission to this year's Big Data Bowl competition. This belongs in the metric track, I should say. So Nick's submission was also metric track this year, and Smith was the undergraduate's track. Yeah, and from Carnegie Mellon, like Greg said, and I'm a second-year PhD student in a statistics and data science department. Okay, let's get started. So I'm gonna quickly give you an overview of traditional metrics for tackling. So the most basic tackling metrics out there are tackles, solo tackles, or assisted tackles, or just assists. These are binary outcomes observed at the end of the play. So these are just box score statistics. And surprisingly, these are not official statistics from the NFL. So at each game, the home team sort of designates a scorekeeper to keep track of these statistics. One thing I should say also is that if you combine these two, so if you just add tackles and assists together, some people sometimes call those combined tackles. And then there exists a few versions of statistics that sort of try to improve these binary outcomes. So stats bombs, when they calculate their combined statistics, combined tackles, they treat an assist as a half as opposed to just a one originally. PFF created something called stops, which I think only tracks the tackles when the play does not end in a positive yardage gained for the offensive team. And PFF also tracks something called missed tackles, which the name itself is pretty explanatory. The common theme of these metrics is that these are only discrete outcomes measured at the play level. And some of them are like for tackles, for example, it's it's based on sort of subjective judgment from the scorekeeper. So there are definitely lots of limitations with these statistics. So in order to evaluate tackling within the play, we decided to think more carefully about the purpose of tackling in American football. So if you go through the NFL rule book, this is the screenshot I took from the website. You see that there's this phrase saying that tackling is an attempt by a defensive player to hold the runner, to halt his advance or bring him to the ground. Okay, so to quickly summarize, so the purpose of tackling is what? That is to halt the forward motion of the ball carrier. And this forward motion can be measured via the velocity of the ball carrier towards the end zone, which can be directly derived using the player tracking index, since we have information about the velocity of the player and also the angle they are motioning. Okay, so the goal of this project is to propose a framework to measure tackling contribution throughout the play. And we also want to assign defensive credit to defenders for halting the ball carrier's forward motion. And this would allow us to eventually derive a continuous metric for defensive performance that sort of moves beyond the traditional binary tackle designation. Okay, so let's touch on the data a little bit. So again, the data came from the 2024 Big Data Bowl, has a theme of tackling. So we have player tracking data. So data collected at a rate of 10 measurements per second. The NFL put RFID chips inside of the shoulder pads of each player and also the football. We have data from the first 9 weeks of the 2022 NFL regular season. And throughout this talk, I will be using an example play, which is a 7-yard run by New York Giants running back Saquon Barkley against the Tennessee Titans from week 1 of 2022. So the data would look like this if you actually view it. So, we have the timestamp for each play, the frame ID, X and Y. So those are just 2D locations of the players. Then we have speed, acceleration, distance travel from the previous frame, with the orientation and also the angle of motion of the players. And one sort of crucial feature here is the event annotations associated with each frame of this play. So we know when the ball is snapped, when the ball is handed off to a running back, when the first contact is made, and then when his tackle is made. And for this analysis, we will focus on everything between the ball snap and a play event. So here we have tackle. You can also have like touchdown, out of bound, fumble, etc. And here's what the example play looks like. So, you have Saquon Barkley when the ball is handed off. There are clearly defenders that contributed to slowing down the running back, but was not credited with a tackle previously by the scorekeeper. So there are multiple defenders involved here in this process, as you might see. So it is necessary to measure this type of contribution at a continuous level. And so this is the goal of our project. So our framework for within play tackling evaluation consists of the following steps. The first step is to identify what we call contact windows. So these are sort of time intervals within a play where the defender has the chance to possibly make contact with the ball carrier. And our definition is that a contact window is a set of consecutive frames where at least one defender is within 1.5 yards of the ball carrier. And we chose this 1.5 yards threshold since it captures a pretty high proportion of the distance between the ball carrier and the closest defender at the moments of first contact and tackles observed from a play tracking area, as you can see from this histogram right here. I would say that this is a very heuristic definition, but I think this is the best we can do with the play tracking data, given we only have the 2D information of the player. With better information like post data, data generated from computer vision, you might be able to come up with a better definition of a contact window. But the other nice thing about this definition is that it can easily be implemented in a media broadcast. So since it doesn't require any modeling tasks here. But again, if you have a better definition, you can simply plug this into our whole framework and simply replace our definition and hopefully doing a slightly better job. So let's go back to the example play. So here I'm just plotting it with this animation. So on top, we have the locations of every player. So Giants, it's in red on offense. Titans, in blue, it's on defense. And notice that the defenders are, the color for each defender can change if they are in the contact window of the ball carrier. So it changed to gold here. And so the contact window is sort of like, so if you draw like a circle of radius 1.5 yards around the ball carrier, then if the defenders are within that threshold, then we say that they're making contact with the ball carrier. And also in the bottom here, we have the velocity of the ball carrier towards the end zone for this play. Where again, that's the y-axis, and on the x-axis is just time. And so for this play, we observed 3 separate contact windows. And again, you can see that multiple defenders can be involved in the contact window. And so it is necessary to measure this type of contribution and sort of assign appropriate credit among these defenders for slowing down the forward motion of the ball carrier. Well, so this brings us to step 2, which is after we have defined this contact window, we want to measure the tackle value of each of those windows. Okay, so in particular, we want to look at the change in velocity relative to where the peak momentum or the peak velocity of the ball carrier is within the play. So that triangle right there is for peak. So it's a triangle. It's peaking. Okay, so let's first look at the first contact window. Okay, notice that the peak ball carrier velocity occurs after the window. Okay, as the ball carrier continues to speed up and gain more velocity towards the end zone after this window. So they will say that this window has 0 value since the ball carrier continues to gain velocity. But for the second window, since the peak velocity occurs prior to this window, we can take the difference in velocity towards the end zone of the ball carrier between the starting and ending time points of this window, and then divide that by the peak velocity value achieved by the ball carrier within this play. And this fraction of reduction in velocity relative to the peak velocity values to give us the notion of the value for this whole concept window. I should note that this is like the base equation. We had some modifications to this given different sort of trajectories of the velocity of the ball carrier. But for this specific play, this calculation can be achieved with this simple equation. And we can do the same thing for concept window number 3 as well. But for, so the same equation, but for illustration purpose, I'm going to move on and use contact window number 2 to illustrate our last step, which is dividing the value of the whole contact window into what we call fractional tackles for each defender involved. So again, so here's contact window 2, and to give you some context, this window spans 4 different frames within this play. So we have those 4 frames plotted down the bottom. And this window involves 2 total players. As you can see, these dots, these circles in gold. We have number 37 in the first 3 frames, and number 51s are in the latter 3 frames. Okay, so they overlap in the 2 middle frames here. Okay, so again, step 2, we have the contact window value already. The first step here is to divide that window value equally across all frames within the window. Okay, so each frame would receive a quarter of the credit here. And then within each frame, we equally divide the frame level value across the players involved in that frame based on how many players there are. So for the first frame, it's only 37, so that so 37 would get all the credit for this frame. Second and third frame, 37 and 51, so they each get half of the credit for of the frame level credit. And then for the last frame, 51 is the only player in the contact window, and so they would get all the credit for that frame. Okay, and then then we can sort of aggregate across the window level by adding the frame level credit for each player to get their specific window level tackle value, and then you can aggregate across the whole play, the game, the season, etc. Okay, so here's the summary of our fractional tackles metric for the example play of the Saquon Barkley play I shown earlier. So previously, if you just look at the box score statistics, only three players had sort of like these labels. So the one person got a tackle credit, one got credit with an assist, and one got a missed tackle. But here we are able to credit 4 additional defenders for sort of contributing to slowing down the ball carrier, so and which effectively downweights the contribution of the people that previously got a tackle and assist. Okay, so far I've presented our framework, and so what I'm going to do now is to present a few sort of validation tests to what we just proposed. So first we have the leaderboard of fractional tackles for all players. So the columns here are what we're going to focus on here are the last 2 columns. So first we have total fractional tackles and then average fractional tackles. So if we just look at total fractional tackles, we see that linebackers are those that have sort of the highest amount of total fractional tackles. So you see names like Roquan Smith, Foyo Luakan, etc. These are names that also finish pretty high in the actual tackles leaderboard in real life in 2022. But if you just look at the average fractional tackles, we see that defensive linemen, so defensive tackles, defensive ends, etc., they actually have higher fractional tackles value on average than the linebacker. So although the linebackers accumulate tackles, our metric captures how the defensive linemen sort of tend to record more consistent stops on the ball carrier, and hence this metric sort of provides a more measurable statistics for defensive linemen, which a position that sort of been lacking sufficient objective measures previously. Next up, we have, let me try to hide this. Oops, how do I hide this? Oh, there we go. All right, so we have this scatter plot here. So what are these axes and data points? So on the y-axis, we have the total fractional players for these defenders, which are the dots here, and on the that should be the y-axis. On the x-axis, we have the total tackles and assists over 2 for these defenders as well. And again, each of these data points are the players calculated by their position group. And the dashed line here is the identity line, which means that if the total fractional tackles for a player exactly equals the total tackles and assists, the data point corresponding to that player would fall on the dashed line. So what we can see here is that despite the strong correlation, total fractional tackles are lower than the total tackles and assists, since most of these data points sort of lie below the dashed line. So this suggests that the traditional stats of tackles and assists sort of overstate the contribution of a defender in terms of halting the forward motion of the ball carrier. The last thing that we have here is some stability plot. So the question of interest here is, does our metric measure the same quantity over time? So in other words, does previous performance predictive of future performance according to our metric? So in the top row here, we have on the y-axis total fractional tackles for the last 5 weeks of the 2020 data, and then on the x-axis the first 4 weeks, and then the first plot is just the overall correlation among these players, and then we also separated this plot by position. So the latter 3 plots are the within position correlations. And then for the purpose of comparisons, we also show the total tackles and assists, the exact same with the exact same plots in the bottom row. And overall, the trend here is that we see that first of all, fractional tackles is repeatable among these defenders, as reflected by this sort of moderately strong correlation of 0.69 in the top left plot. We also see that overall and also within correlation, metric is more predictive of future performance compared to tackles and assists across the board. We just compared these correlation values. A metric all had higher values, and hence it has a higher predicted performance of than tackles and assists. Okay, so just want to quickly wrap up with some discussion. So in this project, we have introduced fractional tackles, which is a new simple continuous metric for defensive performance. One key stat that we found sort of fascinating is that players that made a tackle based on just the play level data do not have the highest fractional tackle in more than 20% of the plays in this sort of 9-week sample. So which is kind of interesting. And one limitation that, as I sort of touched on earlier, is we only have the 2D tracking data, so we don't know whether or not the players are actually making contact with one another. But if we have access to better data, like post data, computer vision data, etc., we might be able to get a better sense of this whole making contact and maybe come up with a better definition of the contact windows. Future direction. So if you happen to check out our big data submission, the title of the submission is momentum-based fractional tackles. But notice in this talk, the title is only fractional tackles, so we dropped the momentum stuff. But so to sort of talk about future directions, here's a picture of 2 running backs that played for the Tennessee Titans back in, I think, 2018. So on the left, we have Dion Lewis, who is only 195 pounds. On the right, we have Derrick Henry, who's 245-ish pounds. So what I want to emphasize here is that size does matter here because, you know, tackling someone like Dion Lewis is not the same as tackling Derrick Henry. And so momentum is actually a better measure of forward progress than just velocity towards the end zone, since the concept of momentum is essentially mass in motion, where it's the product of the player's weight times the velocity. But I want to note that in our framework of creating fractional tackles, replacing velocity with momentum would result in the same answer because we're just, you know, having one quantity on top and we're dividing by that quantity, so the mass of the player would get canceled. So someone pointed out to us at Big Data Bowl, and we were like, yes, that's correct. We should think about simple math in the first place. But we do think there's lots of interesting applications we can do with momentum. We have a project going on right now looking at the change in momentum for the contact window and sort of trying to look at different factors that impact that and so on. So stay tuned for that, I guess. So I want to quickly acknowledge a few people. So we have a full team from CMU, Larry Zhang, Meg Ellingwood, and Ron Yoko. Someone on Twitter gave Ron the nickname, I think, the Nick Saban of football analytics or something like that, which is, I guess, appropriate. Because, but I want to acknowledge them for the whole involvement in this project. I guess thanks to Greg for early conversation at work in Chicago when I was visiting before, I think it was during Thanksgiving last year, and sort of got a few ideas out of that. Also want to acknowledge the Big Data organizers, the data analytics team from the NFL. So Mike, Ali Blake, Tom Bliss, and the rest of the crew for yet another year of sort of fantastic competition. Lots of great submissions this year, and I would encourage everyone to, you know, participate in the Big Data Bowl and future competitions. It's a great way to be involved, not just in sports analytics, but to showcase your data science skill in general. That would be an amazing thing to put on your portfolio. So going to close out with some links. So we have a paper released on archive. I think I put it up there 3 weeks ago, maybe. It's under review. Check out our notebook for Big Data Bowl this year. The code are publicly available on GitHub. You want to contact me? That's my website. Feel free to reach out if you have any questions, and if you're interested in sport analytics, which I think most of you are just since you're here. Check out what CMU has to offer. We have our annual conference every November, and lots of other fun initiatives. So that's all I have, and thank you for your attention.
So we got a question.
I have 3 questions actually. So the first one is like, when you draw the circle is very wrong, do you need to consider some directionality when you attribute the value? For example, if as the defenseman is behind the person, maybe not, but like
So,
probably you don't want to.
For now, no, but I guess we could
But
take
is
that
it
into account. That it's possible. So again, like I mentioned earlier, a definition is very, very simple. It's just like
yeah?
distance based, but you can come up with like a better definition using, like you said, direction, angle, etc.
Okay.
Plug that in and replace, what we had, and then try to see if the results would change. I doubt it would change that much, but I don't know. I haven't done that sort of sensitivity analysis.
Okay, because like your in your study, you're trying to count it as the fraction of the like a velocity drop, forward velocity drop, right?
Yes, towards the end zone.
Yeah. So I'm just that already considered direction. So I'm just thinking about like when you consider how to say the value distribution, should also like for people who behind, you don't distribute any value to the person because they're behind, they're not stopping the. So
Yeah.
that's first thing.
That's a good point. Yeah.
Okay, second thing is about, so if it's a velocity drop, right? And then does it mean that people outside that circle doesn't contribute anything? For example, if there are people already in front of, but they're outside of zone, would they still contribute to the velocity drop?
No, for now, no. For now, if they're outside, we're not assigning any value to them.
Okay.
But
But logically, does it like, sorry.
yeah, I mean that makes sense. And
Okay.
I mean we could like try different definitions of the contact window. But
Okay.
I think if we get like 3D positional data, like post data, that would be the ultimate goal of making this more
Okay.
like appropriate.
Yeah, thank you. And then third question is like, I think you study the correlation between the fractional tackle and then the traditional concept of combined tackle, which is tackle plus half of the assist. And then you saw their correlation. But I mean, that's really good. But then the question would be for example, if a coach or a manager, they look at the leaderboard, they are facing 2 leaderboard. One leaderboard is the fractional tackle leaderboard. Another is the combined.
Traditional, yeah.
Yeah, then which one they should trust more? I mean, logically, fractional tackle is better because it's continuous, but still, like, is there any evidence or support to say, hey, you should consider this better more than the other one?
Yeah, because I think a metric is not just a binary definition where we're defining it based on like the actual definition of tackling, right? Which is stopping the forward motion of the ball carrier. So that's what we use to derive the metric. So that's I guess that's the pitch to the coaches out there. And
so if there's a good example of showing that what combined leaderboard failed to capture but successfully captured in the fraction tackle, I think that would be very helpful, right?
Yeah.
Proof that is.
Yeah, I don't think we looked at any example. I don't know, but that's a good point. It's
Thank you.
should definitely look into that. Yeah, but thank you. That's a good point.
One quick question, then my actual question. Huang, did you use Greg's ideas or did you just do the opposite?
That was not really his idea, was it? I don't know. I mean, we sort of talked, and then I mean, our group also has that idea already, but Greg was like, "Hey, velocity towards whatever," and then we sort of pivoted towards that specific thing and
keyword pivot. Yeah. So my question on the are there any like forward momentum plays where it would be multimodal? So a player gets their peak
Yes.
speed, loses speed, and then regains speed. And
Yeah.
how does
Yes.
how do those come out?
So for our framework currently, so you're saying there are two peaks. I think the right thing to do is actually splitting that play into sort of multiple plays, so that we can say that this running back has sort of multiple lives instead of just one life. This is the idea of like angry runs where you're just running and then you stop and just running angrier, and you have a peak and then you're peaking even higher. But for now, let's say you have a small peak and then a bigger peak, which is ignoring totally what happened previously to that big peak. But that's certainly what we didn't do. But
Do you know how often there is multimodal curves? Like, like
I don't
Or
know
with
the
magnitude?
answer, but we definitely found like a bunch of, not a bunch of, but several
non-zero.
non-zero. Yes.
All right. Who wants to go? Just want to pass it down?
So when you were doing the stability analysis, did you consider doing it like on a per snap basis? Because like I feel like there's kind of a confounding variable where if you're like an inside linebacker for the first how many total games was it? Like the first 8, you compared the first
First
8
9
ver-
weeks. And I should mention that we only consider running back run play, so we're not
Right.
considering catch plays or quarterback scrambles, but just all running back run
Right.
plays.
So you compared like the first 8 weeks to the last 9 weeks or something, right?
Now first 4 versus last 5.
Okay, yeah. First 4 versus last 5. Like, isn't there a confounding variable of just like if you're an inside linebacker, like you're gonna play more snaps in the first 4 weeks, and you're gonna play more snaps in like the weeks, 5 through 9 or 5 through 10 or whatever. 5 through 9. Anyway, so
I think we did look into per snap. I think I looked into that specifically.
just like for stability, like I feel like that's
Yes,
gonna give you.
but
stronger
I get where
square.
you're coming from. Yes, that's probably should also include that in like the revision of the paper or something like that. But yeah,
Right. And then one more. So you said you were talking about more like momentum studies you were doing. Have you looked into like tush push stuff at all, and like how much like the guy behind him weighs versus like he's pushing the.
not that specifically. Because one other thing about the big table this year is that the NFL doesn't want us to do any sort of injury analysis, and then tush push has lots of like implications to injury. So
Oh, okay. Yeah.
but I don't think the samples for tush push is that high.
Right. That makes sense. Yeah.
Think-
I guess we need a couple years of like Jalen Hurts. and
Yeah,
all these
yeah,
guys.
but yeah.
Cool.
So when I was looking at how you were comparing the fractional tackles across like different position groups, I noticed that you grouped both cornerbacks and safeties into
Yeah.
defensive backs.
Exactly.
And usually when you look at like the stat sheet for traditional tackles, you see first, like in terms of like positional groups, there's the linebackers and then there's the safeties, and safeties normally have a lot more like tackles and solo tackles than cornerbacks. I was wondering if you A, looked at the difference in fractional tackles between cornerbacks and safeties, and B, if that matched similar trends for tackles and solo tackles.
No, but that's a good point. I should definitely do that at some point. But yes, your point is well taken. Yeah, thank you. Yeah, I mean,
Okay.
got 5 more minutes until the next session, so just keep going.
Okay. So I noticed I noticed in your fractional like tackle metric, you don't care really much about the time window it takes to complete the tackle. I was wondering if like because for a certain velocity change, if the tackle window takes longer, the offensive person carrying the ball will advance further over that time period. Is there any way of weighting fractional tackles that take less time to complete? Have you thought about that?
That's a good point. I think we briefly thought about the idea of weighted fractional tackles, but no, but we didn't do it. Again, it's for simplicity, but I mean, all the code are out there, so if you want to sort of improve upon this, feel free to, go hard and